Let me first point out that not every machine learning method builds a model. And today I choose to talk about k-nearest neighbors. Maybe this is one of the oldest machine learning methods out there. So typically k-nearest neighbors don't build a model, but they still do some classification. They're able to do classification and regression. So our first ML method is KNN. The main idea of KNN is to use the notion of similarity between examples. The assumption is that two similar examples should have the same labels. And this is something very intuitive. So suppose you have a set of fruits and you want to, if you take a look at two fruits and look at the similarity between them, you could say whether they are likely to be the same category or not. So the two bananas have some similar features such as the length and the width, roughly in the same range of length and width. So we are going to assume that all our examples are points in a d-dimensional space. This is the space of features. So we have data points or examples. These data points are described by a set of features, and they lay in some dimensional space. Just like the case of bananas and apples, we could think that we have the width and the length of the fruits, and we have our data points laying somewhere. So we may have something like all the bananas laying on one side, and all the oranges may be laying simply on the other side based on their feature values of width and length. So k-nearest neighbor uses what we call the standard Euclidean distance. This is the distance between the data points, which means that if I go back to my previous example, the distance between this point and this point would be measured by their values at the x and their values at the y-axis. K-nearest neighbors uses the standard Euclidean distance to define the nearest neighbors. So the principle is very straightforward. So you take two examples, xi and xj. So these are two data points in some d space, and you calculate the distance between two data points by taking their feature values going from 1 to d, right? So you have d dimensions. Just take the difference between their values at each feature, square this, and put everything, the sum, under the square root. So this tells you how far are each point, the point xi from the point xj. There are, of course, other distance metrics, but the most commonly used is the Euclidean distance. The training algorithm is very simple. It simply consists in adding all the examples, x and y, where x is the feature value and y is the label, to the data set D. This simply means store your data. That's all you need to do to make your training. There is no training and no model built at all. Okay? So then the classification stage or classification algorithm consists in the following. So suppose you have your data set of bananas and apples. You store this data set in D, right? In the data set D. You want to use it to predict a new instance. So given another example, let's call it xq for x query. You want to query what would be the label of the new fruit. Suppose you can't see the fruit, so you can't tell whether it's a banana or an orange, but however, you know the length and the width of the fruit. In this case, you're going to just drop this fruit in the middle of all your fruits and see where it falls. If the neighborhood is mostly bananas, then you would classify this fruit as a banana. If the neighborhood is mostly oranges, you would classify the fruit as an orange. So this is a very simple principle. So the idea of the classification, so if you have in our fruit example, suppose you have the length of the fruit and the width of the fruit, and you have all the bananas laying somewhere on this side of the plot, whereas the oranges would lay somewhere maybe here, right? So the idea is, given this x query for which we don't know actually what is the label, let's put it somewhere here, right? So for this point here, we want to see what is in its neighborhood. So this example is xq. We want to be able to find what's yq, and we put a hat because we're going to estimate it based on the data. So this yq is calculated as what? So let's suppose that nkxq means that look in the k neighbors of the x query, of the new examples to classify. And then take the label of all these points in the neighborhood, right? And do a majority voting. So you're going to predict that this fruit here is likely to be an orange. So you're going to define that yq would be equal, in this case, to -1, which is the sign or the label of the fruit that are in the around it. So here's another example. Suppose that you have this configuration in which you have two kinds of fruits, the orange and the blue, right? And the query is the point, the cross here in the middle. How can we classify this point? So we look in the neighborhood, right? So in the case of three nearest neighbors, we're going to look into the three nearest neighbors to the point of the query. In this case, we have two blue and one orange, and you would classify this X query as a blue circle, right? So as I said, k-nearest neighbors don't provide a model. We just store the data and we just put the point in the middle and see where it falls, right? So if we ask whether we could draw an approximate decision boundary to see what actually k-nearest neighbor is doing for k equal 3. So for example, what we could do is to look in the neighborhood, draw this what we can do is to imagine like fictive points around, right? And for each of the data points, let's check whether we could predict the kind of the class of the point. So if I look at this point here, it looks like the nearest neighbor of this point would be something like this point here is the nearest neighbor, this point here is the nearest neighbor, and this point here is the nearest neighbor, right? So this point would be classified as blue. If I take a point here, the nearest neighbors will be this one, and this one, and I would predict that this point is orange. So I could that for a kind of dividing this picture into a set of a grid of points. For each point, I would look into the neighborhood of three neighbors and decide whether it's actually a blue or orange circle. So if I do this, I will come up with the decision boundary that actually is just fictive. We don't really do it in k-nearest neighbors, but look at how nonlinear is this decision boundary. So implicitly, k-nearest neighbors is doing some nonlinear job in identifying the class or predicting the class of examples. So k-nearest neighbors seems very simple and very straightforward. What are the pros and cons of k-nearest neighbors? First of all, the advantages of k-nearest neighbors is that, as you have seen, this is very simple to implement. Store your data, check where your point fits in the data, right? It works very well in practice, and as a matter of fact, it has been used for several decades on different domains. It doesn't require to build a model and makes no assumptions about the distribution of the points. And there is no need to tune the parameters, except maybe k if you want to learn the best optimal k for the nearest neighbors. It can be also extended easily with new examples. So whenever you have a new example that you collect, you just add them to the data set and there is no need to retrain any model. However, they also have disadvantages, and this include that it requires large space to store the entire training set. So suppose with time you're going to collect 3 or 4 millions of fruits, you still have to store this somewhere on your disk. And it's also very slow. So you could imagine when you have a new query, you need to figure out what are the k-nearest neighbors to this point, which means that you're going to calculate the distance between this point and the rest of the data that you have. Given n examples and d features to be general, the method takes about an order of n times d, so n is the number of examples, times d, to run. That's a lot. So for each data point, you need to do a lot of calculation to figure out what are the points in the neighbor. And it also does suffer from what we call the curse of dimensionality, which is that in very high dimensional spaces, so in the case of fruits, we have 3 dimensions, but suppose you collect a lot of features describing the examples, and in this case, the distance becomes meaningless when you move to a very, very high dimensional space. More on it will be on your course on machine learning. Applications of KNN, as I said, are numerous. This include information retrieval when you try to search a text in a search engine. This text is the system will be looking for similarity between your text and the existing web pages. Handwritten character classification using k-nearest neighbors has been also out there for a long time. Recommender systems, example, users like you may like the same movies, so you need to find a similarity between you and the other users, which implies that you're going to look for the k-nearest neighbors or the k closest people that have similar features like yourself. Breast cancer diagnosis, medical data mining, like finding patients with similar symptoms. And in general, pattern recognition in general has used a lot in the past k-nearest neighbors, and it's still being used today for its simplicity and effectiveness. Let's go back to our training and testing process. So we said that we have a training set. We deploy some machine learning methods. We have seen KNN as an example. we build some model, right? And given this model, we can make a prediction. You have some input and you can get some output. Now, how can we be confident that this model F is good enough? We calculate some kinds of errors to be able to assess whether our model is good or not. So for this purpose, we're going to calculate what we call the in-sample error, or the training error, or also empirical error or risk. The training error is a measure that tells you how many errors is your model F doing on the training data itself, right? So we call it E-train of F, which means that given the model that you learn, how many errors you're making. A way to do it is to calculate how much loss of information you're getting. So suppose that, remember that we're in the case of supervised learning, we are trying to find a function F that goes from the feature values to the label Y, right? So this function F means that when I apply this function F on X on a new feature value, I make a prediction. So this is the prediction. But for training data, it happens that I also have the true label available, and this is Y, right? So if I take these two quantities, for each training example, I compare what the true label is, and I compare that to what? To what the model is telling me. So I compare Y to the model F applied on the feature values X. So I will define this difference to be actually what we call a loss. How much information I lost based on the labels that is the true label versus the predicted label by F. And I could sum this up over all the training example I have. So take the prediction made on your training examples using your model F and calculate some loss between the true label and the predicted label. There are different kinds of loss functions. In a classification setting, for example, we could calculate the loss between the true label and the predicted label as 1 if the sign of the true label and the predicted label are different, which means that it was a banana and your model F predicted it as an orange, or vice versa. So we are going to add 1 to the loss whenever we make a mistake. So this means simply that there was a mistake made on the model by the model F on predicting the class of the element xi. If there is no mistake, in this case, we're just going to sum up 0, to add 0 to the loss. Another kind of loss function that's actually also suited for regression is the loss that simply makes a difference between the true label and the predicted label f of xi. So we square it just not to worry about the sign of the difference. So if you have if you have an example for which you have a label and you have a prediction, you can simply do the difference between the label and the predicted label. We also hope that the error on the test set, also called the out-of-sample error, will be small enough.